Hello students, welcome back to Misostudy video classes. And in this video what we are going to discuss, which is mentioned in front of your this screen, that is CBSE pattern question exercise, and that too for a very important chapter, that is electromagnetic induction. Fine. So the methodology is going to be same as I am following, like one by one different marks questions you will get, and I will tell you how you should provide the answer in your actual exam so that you can earn more marks, get more marks. Fine. So let us start the discussion, because as such nothing is new for me to explain you, and also nothing is as such new for you to learn. Fine. Methodology is as exactly similar. So here it is question number 1, and as usual I would like to mention that these points 1 mark, 2 mark, 3 mark or any instruction at the first page of the question paper, front of the question paper or in between the questions, please take care of that. So question number 1 and 2 as usual for 2 marks. Now this question is, does change in magnetic flux induces electromotive force or current? So it is a confusion in the mind that flux change, that is phi b, is giving me basically EMF or current. So simple, till now we learned that induced EMF is equal to minus d phi b by dt. Fine. So from here this induced EMF is coming first into picture, then induced current is I induced, that is this I induced is like I induced is equal to this upon load resistance or resistance. So the answer should be flux phi, this induced EMF will come after the changes in magnetic flux will take place. Current is not the first thing that will come into the situation. Okay. So here now it is going to be question number 1, and in 1 mark as usual I am telling you, you just have to mention some basic points. So here with the help of this small remote I am changing the question, and it is your second question. If a wire is kept in east-west direction is dropped freely, what will happen? Now actually they want to know a very simple and fundamental aspect, whether you have the idea of two components of Earth's magnetic field or not. Fine. So you know there are two components of the Earth's magnetic field. One is BH, horizontal component, fine, that is like in this direction horizontally, and another is VB, that is vertical component. So the direction of vertical component is like this. Fine. Now when the wire will start falling in east-west direction, so their question is what will happen? So the answer should be, at the ends of the wire an induced EMF will appear or potential difference will develop. Fine. Why the potential difference will develop? Because, not because of VB but because of BH, because the wire, fine, when it will fall, so it will cut these lines, horizontal lines. Because of this reason there will be a potential difference at the two ends of wire, let us say wire end A, wire end B. Fine. So what your answer should be? Your answer should be, when this wire will start falling freely, because it will cut the BH, that is horizontal component of Earth's magnetic field, so it will induced EMF will come into picture. Fine. Now it comes question number 3, and in question number 3 you know 2 marks, fine, not only 3 but question number 4 also. So these two questions are for 2 marks each. So, show that rate of change of magnetic flux has the same units as induced EMF. Actually, when I was explaining various theoretical topics of this chapter, at that point of time, even I emphasized a lot that you should know the dimensional formula of L, self inductance, M, mutual inductance, induced EMF, voltage, potential. I mean, all these type of quantities, dimensional formula you should know. So, here show that rate of change of magnetic flux, rate of change of magnetic flux has the same units as induced EMF. So, do not you think both are correlated? Basically, we are saying left hand and right hand part. Actually, EMF is phi b by dt. Now, you have to show. Fine. So, you cannot say okay, because they are correlated, so dimensional formula is going to be equal because left hand right hand parts are equal or something like that. Logical approach is you show it. For 1 mark you show it this, and for 1 mark you showed like this. So, from here let us start from this box. If I will start from this box, then I can write it down as B A upon T, because cos theta no dimensional formula. And about induced EMF is nothing but similar to V. So, the dimensional formula of potential is going to be equal to the dimensional formula of this quantity and the dimensional formula of this. So, both sides you can say now they are simple, equal to each other. Let us say you do not have time, just for the sake of simplicity I am telling you. Then simply you can say, in physics, two quantities proven to be correct, they can be equal to each other only if dimensionally they are same. Left hand side dimensional formula is equal to right hand side dimensional formula, but that will be like somehow you are forcing your answer. So, better to show like this, because it is mentioned show. Fine. So, it was question number 3 and it was for 2 marks. So, I hope getting these 2 marks is not a difficult part. Fine. 1 mark you can show this induced EMF, and for next 1 marks you can show this second part, that is d phi by dt. Then comes question number 4. It is a type of numerical, and whenever you are getting any numerical, then you should try to pick that numerical if the choice is there. Reason is simple. Numericals are in general easy, and if you solve them correctly without any units error, without any calculation error, then possibility is for scoring full marks. Fine. In theoretical answer, if it may be possible like that you are writing and then you are missing 1 or 2 points. So, maybe half or 1 marks may be deducted. Okay. So, this is the situation, but if you are 100% sure that you can solve this numerical, only then pick that numerical. Otherwise, better is to at least attain few marks rather than losing full marks. Fine. So, a circular brass loop of radius A and resistance R is placed with its plane perpendicular to a magnetic field. Fine. Let me allow to draw the diagram. Actually, this is a circular brass loop. Fine. And it is placed, its radius is, I think I should draw it more clearly. First read the second line also. The magnetic field is given by like this. So, you can say magnetic field is changing with respect to angle, time. Fine. Now, let us draw the diagram. So, just take a look. This is a circular brass loop and radius is A and resistance is R. It is like that. I am observing it from the top. Fine. Okay. Now, magnetic field is perpendicular. So, as it is not mentioned plane perpendicular to a magnetic field, so it is your liberty. Either you can put the magnetic field like this or like this. So, let us say magnetic field is like this. Fine, as it is not given, so this is perpendicular, not a problem. Fine. Because area is not changing, because theta is not changing, but magnetic field itself varying, itself changing. So, flux change will take place and then induced current. Now, first you have to calculate the induced EMF due to flux change. Then I will calculate the current as using the formula I induced is equal to by R. Fine. So, our first target is to calculate induced EMF. Fine. So, from here I can write it down as this relation I is equal to this much R is equal to d phi b by dt upon R. No problem, simple relation. Now, consider this magnetic field. Actually, simple trick is used over here, very simple trick, that is d phi b by dt is equal to d by dt, and then this b a is pi a square. That is not a problem, you should put it outside rather. Fine. So, yes, you should put it outside of it. So, it is going to be like this, pi a square d by dt of b naught sine omega t. Fine. Simply differentiate it, you will get this I finally is equal to minus a omega b naught cos omega t upon R. I used pi a square, you can also, fine, no problem. So, for 2 marks this question is very simple question, okay. It is like that, you will enjoy while you will solve this question, basic formula and then basic, very fundamental and basic approach for getting the answer. So, now again our board is clean and green and we are ready to discuss another set of questions. Fine. So, here comes question number 5 and 6 and both these questions are for 3 marks, and induced EMF has no direction of its own. Explain. Basically, they want to know Lenz's law, because I very specifically mention Faraday's law of electromagnetic induction, that if you want to find the direction you have to use Lenz's law, because your first Faraday's law is based upon conservation of energy principle. Fine. So, this particular Lenz's law, basically it is the way of asking indirectly Lenz's law. So, here you have to explain Lenz's law, because in Faraday's law it is not mentioned the direction. Fine. So, because of this reason, actually if in this question you are writing like this only Lenz's law, then some examiner may deduct 1 mark or so. So, better you mention the answer of this question like this: as per the Faraday's law of electromagnetic induction, the direction of this induced EMF is not defined, because if flux change is like in one direction, then it will oppose that change, or if it is in other direction it will oppose that change. So, vice versa, you can say clockwise anti-clockwise type of situation. So, it has its no own direction, it behaves as per the rate of flux change. Then you can mention Lenz's law and accordingly you can explain the direction. Fine. So, this a simple theoretical question which at least twice or thrice I explained in my videos of this chapter. I hope you are regularly watching these videos at least once in a while. Fine. Then comes question number 6, define mutual inductance. Specifically, I prepared one complete video on this mutual inductance, complete video on mutual inductance. And if you are regularly watching these videos, you will find yourself in a very simple and comfortable situation. But just for the sake of mentioning, you have to draw two diagrams. Fine. First coil, and you have to connect a galvanometer over here, that is known as coil S, secondary coil, and then you have another coil here, and then a key is connected. Fine. So this is primary coil. K E. Create this diagram and explain this mutual inductance, that when you press the key, current will start flowing in this primary coil. So induced EMF, let us start from the magnetic field. So magnetic field will start enhancing, accordingly flux will change, accordingly induced EMF will come into picture. So something will take place over here. Fine. And then when we open the switch, this key, then current will start reducing, magnetic field will start reducing, so it will oppose. So this type I prepared the entire video, and it was mentioned like phi is directly proportional to I induced. Then I mentioned phi is equal to Mi, where M is mutual inductance. Fine. And then it was explained with the dimensional formula, units, all these things. So my request is watch that videos. Actually, in general in this chapter, all teachers explained self-inductance, mutual inductance together, but I bifurcated. I devoted one complete lecture onto self-inductance, one complete lecture to mutual inductance. Fine. This is very important question. And that's why again and again I would like to request all of you, be regular with our videos. You will not find anything difficult. Fine. Then comes question number 7, and this question is for 4 marks. What are ED currents? Discuss briefly any 2 applications of ED currents. One complete video for 30 minutes. I completed this entire topic, experiments, what exactly ED currents, and how you can mention some applications. I explained over there that flux associated with any coil, if changing, then induced current will come into picture. Fine. But as per the one scientist Foucault, he said if flux associated with a, you can say, a conducting object, fine, then in that particular object currents will form whirlpools, and that is defined as ED currents. Fine. In application you can mention like induction motor, then induction furnace, then brakes in rails, that is also I mentioned. So all in all, I want that I created these 3 videos, ED currents and their applications, then your self inductance, then your mutual inductance. Once again I am suggesting you please go through with these videos. Perfect answer, because questions you will definitely get in this format in your class 12th exam. Fine. So if you will follow my simple advice, you will definitely come out from your examination hall not by smiling but laughing. Okay, choice is yours. You want to come out with gloomy face, or smiling face, or laughing face. Fine. Then comes question number 8. 8 to 10 means question number 8, 9, 10. All are 5 marks question, big questions. Deduce an expression for the mutual inductance of 2 long coaxial solenoids. Fine. Actually, in the video where I explained mutual inductance, I mentioned two specific cases, and this is one case. And believe it or not, when I was explaining these topics, I was not aware about these questions. So, it is not like that I prepared my videos using, keeping in mind these questions. But after watching those videos, you will find that not even a single question is beyond those videos. Fine. So, in this I specifically mentioned with the help of a diagram this type of relation. M12 is equal to mu naught N1 N2 A by L type of relation, then M21 is equal to same relation, then M is equal to M12 is equal to M21. All those students who are regularly watching our videos, they will say, oh, it's so simple. Here the only change is, because I assumed both the radius same, here it is changed, so it is A1 and next is A2. This is the only difference, slight change, nothing else. Fine. So, all these points, all these questions, you after watching our videos, do one thing, it's a bet with you. Pick any paper of any board exams, fine, and try to find out, is there any question in those papers which is beyond these videos, the topics that we explained? No. Now, question number 9. A magnetic field of flux density this much, that is B, acts normal to 80 turn coil, and this is a basic numerical of 0.10, that is A. Fine. Find the EMF induced in it if this coil is removed from the field in 0.1 second. So, very simple question. I will write down the direct formula, NA B2 minus B1, actually it is delta B upon time. Fine. Now, N is directly mentioned, A is directly mentioned. What about B2? Finally 0. B1 is given, so put the values over here. I hope you will get the answer as, I solved it with these numbers, 8 volt. So, it is a fundamental question. Normally, why I am putting these questions? The tendency of the students is like this. Moment they observe the numerical, oh, it is difficult, let us move away. At least read it once, think, you will say, oh, so simple question. So, shun this habit of skipping the questions, fine. At least once try to get friendly with the question, theoretical question or numerical question. So, it was your question number 9, that is for 5 marks. So, that is why I used to tell you, when you are solving a numerical, there is a probability you will score full marks. And then question number 10, slightly twisted. Magnetic flux of 5 microweber is linked with the coil when a current of 1 milliampere flows through it. What is self-inductance of the coil? I am sure good amount of students will not able to recall the formula. So, that is why I mentioned this question. So, basic question, free of cost, full marks. And this is what? Phi. Phi is what? BA, simple. So, magnetic flux of 5 microweber. So, basically they are not talking about B, but they are talking about, please be careful, flux, that is phi itself. Phi given, I given, I, you have to just calculate L. So simple. Okay. So, these things are not as difficult as you assume. So, it was a basic discussion of all these 10 questions based upon this chapter of electromagnetic induction. Once again, I would like to request all of you, please go through with this chapter in totality. I hope you will find yourself in a very comfortable position. So, very soon I will be coming back with some new useful videos. Till then, take care of yourself. Thanks a lot.